The name we can understand that it is electricity and chemical energy. Okay, so both are combined together. So in this branch, what we do, we deal with the interrelationship between the chemical energy and the electrical energy. So chemical energy, that is coming from the spontaneous chemical reactions. Okay, and by applying electric energy also, we can perform those chemical reactions which are normally, under normal condition, non-spontaneous. Okay, so both are possible. By applying chemical energy, we can generate electrical energy, and by applying electrical energy, we can generate chemical energy. So both are possible. So it is the study of chemical processes that cause electrons to move. So here electrons will be in moving condition. Okay, and this movement of electrons is actually the electricity. Okay, now the flow of electrons, if it is left hand side to right hand side, then the direction of current, it is the opposite. This is current electron movement direction, and this is current movement direction. Okay, so this movement of electrons, that is the electricity, and it can be generated by movement of electrons from one element to another element. Now this from one element to another element, this movement, this type of reaction is known as redox reaction. Now redox, this term is basically the combination of reduction and oxidation reaction. So suppose there are two components, A and B. So B is supplying electron towards A is supplying electrons towards B, and B is accepting electron. That means the process of donation of electron, it is the reducing capacity, and as B is accepting electron, it is the oxidizing capacity. So the acceptance of electron, that is oxidation, and the donation of electron, that will be reduction. So here A, after the showing the reducing property, A itself will be oxidized. So the species which is reducing other species, it will itself be oxidized by B. So A is oxidized by B and B is reduced by A. So whenever there is any oxidation, there must be any reduction, because if some species is giving electron, obviously some other species have to accept the electron, right? So it is related to our biological system also. That means it is a very interdisciplinary subject. Okay, its application is huge. The transmission of sensory signal in our body from brain to other parts, that is also having some electrochemical origin. Now this branch, actually this part of the subject, this can have two branches. Now that depends on this interrelationship. So when we are converting chemical energy to electrical energy, then there is one branch, and when we are doing the opposite one, that is from electrical energy we are making chemical energy, then there will be another branch. So mainly it is divided in two branches. So what are those two branches? Conversion of chemical energy to electrical energy. Here we produce electricity, that is we produce movement of electrons. How? By the energy which is released during spontaneous chemical reaction. So here the chemical reaction is spontaneous, and from this spontaneous reaction, the movement of electron that is occurring, that is from one species to another, that movement of electron is generating the electricity. And the another possibility is obviously the opposite one, that is now conversion of electrical energy to chemical energy. So there are some reactions which are spontaneous, but there may be some reactions which are not spontaneous. Okay, so suppose for example A and B reacting together and they are producing C plus D. Now the forward movement, that is from A and B, you are getting C and D, this is spontaneous. So obviously the opposite reaction, that is C plus D to A plus B, that is not spontaneous. Okay, so when we are moving from left hand side to right hand side, as here energy is released, so that energy can be utilized for production of electricity. But suppose we want to do the opposite reaction, that is now we want to make A and B starting from C and D. but that reaction is not spontaneous. So what we have to do? Now we have to supply electrical energy. So we will make the C and D, these two, to react to each other forcefully so that they can produce A and B, which is under normal condition not spontaneous. But by applying electrical energy, we can make this non-spontaneous reaction spontaneous. Okay, so this is the use of electrical energy to bring about non-spontaneous chemical reactions. Though in this whole discussion, main focus will be on this first one, that is mainly present in the syllabus. But here in the second branch, that is conversion of electrical energy to chemical energy, this is mainly used for production of some chemicals. Suppose those chemicals, if we want to make under normal condition, that is not very easy to do. So in that case, what we can do? We can use electrical energy, and it is, remember, it is also pollution free, because there is no unnecessary harsh chemicals or like that anything is produced. So that is why it is also pollution free. That is another advantage of this second part, that is when we use electrical energy to bring about chemical energy. Okay, now all these processes, that is in conversion of chemical energy to electrical and vice versa, all these are done in a particular cell which is known as electrochemical cell. So from electrochemistry we are getting the name electrochemical cell. So in this cell, electrical energy using a chemical process and vice versa, both can be done. So this cell is known as electrochemical cell. Now as there are two branches of chemistry, that is conversion of electrical to chemical and vice versa, so obviously there will be two types of electrochemical cell, right? So one type, that is galvanic cell, it is also called as voltaic cell. Try to remember both the names, because in some books or in some places you can find one name and in another places you will find another name. Okay, so it is better you remember both the names. Galvanic, it is also written as voltaic cell. So in this cell, what we do? We use spontaneous reactions so that we can generate electrical energy. And in the electrolytic cell, the opposite thing we do. That is, by applying electrical energy, we can do those reactions which are under normal condition, not spontaneous. So two types of electrochemical cell. Now some terms we have to be acquainted of, which is electrolyte, electrode, because these terms it will be used several times in this chapter. Okay, so what is electrolyte? So electrolyte is a substance in which electrodes are dipped. Now what is electrode? Now we will come to that point later. Okay, so just remember, electrolyte is a substance in which electrodes are dipped. Now this electrolyte, it may be aqueous solution or it may be infused state. Okay, so it is in melted condition. So both are possible. We can keep it in aqueous solution or fused state. It liberates ion. So electrolyte, it produces ions, and these ions are actually carrying the electrons, and movement of electron, that is the electrical current. Okay, so here ions are actually acting as carriers. Now what are those substances that can act as electrolyte? It is actually all the acids, bases and salts, because all these under fused condition or aqueous condition, they can produce ion. So the purpose here is to produce ion. If there is no ion, there is no electrical current generation possible. So there must be ions, and electrolytes can produce ions. That is the main thing. Okay, now there may be some strong electrolytes, some weak electrolytes. So strong electrolyte means their dissociation will be complete, 100% dissociation. But if it is weak electrolyte, it will not be 100% dissociation. Fine. Now what is non-electrolyte? Obviously, which in aqueous solution or fused state does not liberate ions. That means it is not possible for it to allow the electric current to pass through it, because they cannot produce ions. Okay, so this is non-electrolyte. So mostly we will use electrolyte, because if we use non-electrolyte, then purpose will not be fulfilled. Okay, now what is electrode? So electrodes are mainly, you will see, it is a rod or strip which is made of metal, but it is not necessary that the metal has to take part in the reaction always. So it may be taking part, it may not be. So all this will be clear in later discussion, because when we will see what are the different types of electrode. But right now we have to understand that electrodes are dipped in electrolyte, and there are two types of electrode. Conductive electrode, one is anode, another one is cathode. So how we will define these two, anode and cathode? So anode is defined as the electrode where oxidation occurs. So always whether it is galvanic cell or electrolytic cell, that is not important, but the important thing is, the common point is, in both cases, in anode oxidation is taking place, and in cathode there is reduction taking place. Okay, now these electrons, it can be made from any sufficiently conductive material, so it must be conductive, otherwise how electron will move. Now metals are okay, semiconductors can be used, graphite can be used, and even conductive polymers. Now these metals, it may be inert metal which is not taking part in reaction, for example platinum, because it is very stable under normal condition, and there may be some reactive metals which is taking part in the reaction. Now in between these electrodes there is electrolyte containing the ions that can freely move. So there is electrolyte in aqueous condition or fused state, and two electrodes named anode and cathode are dipped into it, and in anode there is oxidation, in cathode there is reduction. Fine. EMF, that is cell electromotive force. So this term will be used again and again. So what is EMF? So in electrode electrolyte interface, suppose we have electrolyte and we have dipped electrode. Now in the interface, what happens? There is a tendency of the metal ions from the solution. Suppose in the solution there is metal ion M+. So what it will do? There is a tendency of the metal ions from the solution to deposit on the metal electrode. Okay. Suppose in the metal electrode there is presence of electron, and obviously the positively charged metal that will be attracted towards this electrode. So there will be accumulation of positive charge, as the cations will deposit on the metal electron and it will try to make it positively charged, and at the same time metal atoms of the electrode has a tendency to go into the solution as ions. So when the metal atoms that is in zero oxidation state in the electrode, they are going into the solution in the form of ions, that is suppose M to M+, then what will happen? Now the electrode, there will be the remaining electrons that this metal has left. So this leave behind the electrons at the electron, trying to make it negatively charged. So as there is now accumulation of electron, it will be negatively charged. Okay. So in one electrode there is accumulation of positive charge, in another electrode there is accumulation of negative charge, because oxidation, reduction both are going on simultaneously, right? So that is why a potential difference now will be developed between the electrode and electrolyte, and this is called electrode potential. Fine. Now when the concentrations of all the species involved in the half cell, now what is half cell? As I am saying that there is oxidation reduction both going on simultaneously, so it is the complete cell. But if you consider individually the oxidation reaction and the reduction reaction, then these two are individually will be called half cell, and the species that are involved in the half cell reactions, if it is unity, suppose 1 molar, then the corresponding electrode potential, that is known as standard electrode potential. So try to understand the difference. If it is simply electrode potential, then no conditions are mentioned related to concentration, but when you have fixed the concentration to unity, that is 1 molar, then it will be standard electrode potential. So standard electrode potential, it is very required because there will be several systems. So if their concentration we have not fixed, and there will be electrode potential, it is dependent on concentration. Okay, so if you have not fixed the concentration, we cannot compare the electrode potential of several species. Okay, suppose A is converted to A plus. This is one system. B is converted to B plus. C is converted to C plus. So there are several systems. So if we have not fixed the concentration, how we can compare their electrode potential? So that is why standard electrode potential is important. So here concentration is fixed. Now when concentration is fixed, as electrode potential it is dependent on concentration. So now we can compare the electrode potential of all these species. Okay. The cell potential is the difference between the electrode potential, that is reduction potential of the cathode and anode, which will be, and if you are thinking that reduction potential of the cathode and why not oxidation potential of the anode, so what we do, we actually consider by convention, it is always the reduction potential which is considered, not oxidation potential, just to remove the confusion. So if it is specifically mentioned reduction potential, it is fine, but if it is not specifically mentioned, then by default you can consider it as reduction potential, because that is the convention of IUPAC. Fine. So cell potential, it will be the difference between the electrode potential, which is written in bracket reduction potential. So here we have not mentioned anything, so you have to understand it as it is reduction potential. So suppose in the cathode there is A plus system present. That means in cathode A plus is reduced to A, and in anode suppose B is oxidized to B plus. Fine, but it doesn't mean that we have to consider reduction potential of this and oxidation potential of this. No, you will consider reduction potential for both, and then we can compare. And the difference between these two, suppose it is for cathode, it is for anode, the difference between cathode reduction potential and anode reduction potential, that is the cell potential, and it is also called cell electromotive potential of the cell when no current is drawn through the cell. Okay, so when the system it is not under on condition, then the corresponding cell potential we will call it cell electromotive potential, when no current is drawn through the cell, that is no electron movement is going on. Under that condition it will be called EMF. Now though we are saying that EMF electromotive force, we are using the term force, but don't think it is force. And the unit of force is in SI, it is Newton, and if it is CGS it is dyne. Okay, but we do not use the Newton unit, because though we are saying it is force, but actually it is not force. So it is not force and it is not measured by Newton unit. So what is the unit? The unit is actually joule per coulomb, and this is actually volt. So joule per coulomb means coulomb is the unit of charge and joule is the unit of energy, or it may be work done also. So when C is 1, that means J by C, the denominator is 1, that means the EMF will be directly equal to J. So it is the work done by the source in driving a unit charge. Unit charge means C is 1. So in driving a unit charge around a complete circuit, the work that we have that has to be done by the source, that is actually the EMF. So when C is 1, then J will be the corresponding EMF, and it is actually volt. So joule per coulomb, it is volt. Okay. Now we will consider first galvanic cell. So galvanic cell is basically where we are converting chemical energy to electrical energy. Okay, so here we will use spontaneous chemical reactions so that the released energy can be used to produce the movement, to make the electron move. Okay, the galvanic cell transforms the energy released by a spontaneous redox reaction. Redox reaction means oxidation reduction reaction simultaneously going on into electrical energy, and this electrical energy can be used to perform work. Now there will be a oxidation half reaction and a reduction half reaction, and there is separate compartment for that. where oxidation and reduction going on, and these are connected by external electrical circuit. So you can see this is one compartment which is anode, this is another compartment which is cathode. Here oxidation is going on, here reduction is going on. So after oxidation, the electron that will be left by the system. Okay, so suppose here B plus, B is converted to B plus. That means electron is left by this B. So that electron, it will be now moving through the electrical circuit and it will go to cathode. Now in cathode there is A plus will be converted to A by accepting this electron. So here reduction is going on, and in between these two there is electrolyte. Now a second connection is also present, though the second connection is not shown here, that will be shown in other slide, but a second connection is also there sometimes in between these two here. Okay, so this allows ions to flow between the compartments. So there is one compartment here, another compartment here. You can see the dotted line. This is actually the separation line. So this second connection is also required. And why it is required? To maintain electrical neutrality. Because when in the left hand side B is gradually converted to B plus, there will be excess amount of positive charge, and here as A plus is converted to A and electrons are there, so there will be excess amount of negative charge, because when you are using the solution of B, obviously there is a counter anion of B. Suppose zinc sulfate, so if Zn is converted to Zn2 plus, sulfate ion will be there, so there will be that is amount of Zn2 plus is increasing here. And in the right hand side, suppose here we have copper sulfate. Now copper 2 plus is converted to Cu, so now there will be lack of positive charge. So to balance both sides the charge, what we do, we keep a neutral compound here. Okay, mostly it is called salt bridge. Now what is salt bridge? The picture will be shown later, but in the salt bridge there is a compound present, mostly it is KCl, NaCl, so K plus and Cl minus. So when there is excess positive charge, the corresponding anion can move towards that side, and when there is excess negative charge, then the K plus can move towards that side. So this is the purpose of the second connection. It allows the ions to flow between the compartment, is required to maintain electrical neutrality. Otherwise, in one side there will be excess positive charge, another side there will be excess negative charge. Now this KCl, don't think they will take it, that is they will not take part in the reaction. Their purpose that is why we have taken them, the purpose is solely to maintain the electrical neutrality. They are not taking part in reaction. The potential difference between the electrodes, that is cathode and anode, that is causing the electrons to flow from the reductant to the oxidant. So what is reductant? Reductant is this species, that is B here is reductant, because it is itself is oxidized, that is why it is reductant. Reductant means reducing species and oxidant means oxidizing species. So here A plus is oxidizing B to B plus, and B is reducing A plus to A. Okay, and as electrons are passed through this circuit, then current is generated. Okay, and sometimes here also a voltmeter is kept, and in this voltmeter we can see what is the value of the this cell potential value that we can watch in the voltmeter. Fine. So this is the galvanic cell representation in a very simple form. So here the basic things that you have to remember: anode is present, cathode is present. In anode there is oxidation reaction, in cathode there is reduction reaction. Both are dipped in separate compartment, and there is a outside connection which is through the electrical circuit, and there is a second connection which is between these two compartment, and that is mostly known as salt bridge. So now see, this is a detailed representation of galvanic cell. Now in the previous slide you have seen the general picture of galvanic cell, because we have not mentioned any particular species, whether it is that is any particular metal or salt, but now we will mention that is specific example we will take. And this is also known as Daniell. So Daniell is a special example under galvanic cell. So Daniell cell is galvanic cell, but it is not that all galvanic cells are Daniell. So Daniell is a specific example under galvanic cell. Okay, that is one of the cell type of cell under electrochemical cell, because there are two types, galvanic and electrolytic. Electrolytic we have not discussed yet, but we have started from galvanic, and under galvanic there is Daniell. So this is the most common example that is used. So here in the anode, what we have? We have Zn solid. So Zn solid, that is the electrode. And in this compartment we have taken zinc nitrate solution, aqueous solution. That means here we have Zn2 plus ion and nitrate ion. And in the right hand side we have taken copper electrode, which is cathode electrode. It is solid copper, that is neutral metal copper. And in the compartment we have taken the electrolyte copper nitrate. See, this is salt. We have said that we can use acid, bases or salts as electrolyte. Mostly you will see salts. So here we have taken two salts. One is zinc nitrate electrolyte, another one is copper nitrate electrolyte. So in the left hand side, oxidation reaction is going on. So Zn is in the electrode, Zn is present, here copper is present. So Zn is converted to Zn2 plus. So now in the medium, amount of Zn2 plus will increase. And in the right hand side, and remember, by general convention, you will always find anode in the left hand side, cathode in the right hand side. In some cases you may find the opposite, but it is a general convention that is followed. Anode left hand side, cathode right hand side. So in the cathode side, copper 2 plus in the solution. Here we have copper 2 plus. So copper 2 plus is accepting electron, and these electrons are actually the electrons that is provided by zinc. So here reductant is zinc and copper 2 plus is oxidant. Now electrons which is left by Zn, that is passing through here, and ultimately it is moving towards Cu2 plus, which is present here. Now see, this is the second connection that we have already said. So in this second connection we have taken this type of inverted U-tube U-shaped tube. Okay, so this NO3, here we have taken KNO3, that is potassium nitrate, NO3 minus and K plus, containing KNO3 aqueous. Now in this tube there is normally a gel type of material there, and the two terminal, that is open terminal, that is fixed by glass wool plug, that is allowing ions to pass, but not the solution. That is, we are not, our purpose is that only ions can move, but not the solution. Okay, so glass wool is kept, and inside there is a gel type of material. So NO3, when there will be excess positive charge in the right hand side, left hand side compartment, then the anionic part of salt bridge that can move towards it, so that there is electrical neutrality maintained. And when there will be excess negative charge, because copper 2 plus will be gradually consumed, so there will be excess negative charge, so K plus can move towards this side to balance this excess negative charge. Now what reaction is going on here, that is here shown in a large picture. So here Zn, which is Zn atom, which is present in the electrode. This is the electrode surface. All these are Zn atom. So this Zn, it is converted to now Zn2 plus, which is in the electrolyte, and the electrons that is move towards this circuit, because this electron has to move towards copper 2 plus. Now what is going on here? Here this copper 2 plus, which is present in the electrolyte, this copper 2 plus will gain this electron that is coming from zinc side, and it will be reduced to copper. So gradually there will be deposition of copper on this electrode, and this side the electrode gradually there will be corrosion, so it will reduce in size, and the right hand side copper electrode, it will grow in size. Okay, because Cu2 plus is converted to metallic copper. Now as we have said that when concentration is fixed to 1 molar, then the corresponding that electrode potential, it will be called standard electrode potential. In short, you can call SEP. So if the concentration of Zn2 plus and Cu2 plus both are 1 molar, that is, we are talking about the electrolyte concentration. If both are 1 molar each, then the EMF of the Daniell cell, it is observed that it is 1.1 volt. Okay, this is the value that will be observed in the voltmeter if there is a voltmeter. So this is the value of standard electrode potential of Zn copper system. Okay, so it is the combined value of these two. Don't think it is the individual value of the half cell, it is the combined value of the two half reaction. And now suppose you are doing an external opposing EMF, you are applying EMF which is greater than 1.1. Now what will happen? If this is the case, then the reverse cell reaction will take place. So here ultimately what reaction is taking place? If you add these two reaction, 2 electron both side will be cancelled, because here 2 electron on the right hand side, here 2 electron in the left hand side. So ultimately the reaction that you will get is Zn plus Cu2 plus equal to Zn2 plus and Cu. But suppose if you are forcefully applying some extra volt which is greater than 1.1, now what will happen? The reverse reaction will take place, which under normal condition is not spontaneous. Spontaneous is when we are moving from this side to this side, that is spontaneous. But if you want to move in the reverse direction, now you have to apply greater voltage, I mean greater than 1.1 voltage, that EMF we have to apply. So that then the reaction, it will be in the reverse direction. And you can think that it is as if conversion of electrical energy to chemical energy. Okay, at first when we are discussing Daniell cell, it is simply conversion of chemical energy to electrical energy, because electron is produced by Zn. But now if we forcefully applying external opposing EMF greater than 1.1, now the reverse reaction will take place. That means now electrical energy is applied to make forcefully the chemical energy, because the opposite reaction is not spontaneous. So it is as if the another cell that we are going to discuss, which is electrolytic cell. So electrolytic cell is actually used for that purpose. So now it will behave as if in electrolytic cell. And remember, this is also called reversible cell, because when you are applying greater volt than this value, then reaction will be reversed. So that is why it is also known as reversible cell. So Daniell cell is reversible cell. Fine. Now we will go into the detail of salt bridge. So here we have the same picture, but we have highlighted in the salt bridge region. Okay, the salt bridge helps to prevent net accumulation of positive and negative charge on both sides. That I have already said. So without it, suppose you are not using this salt bridge, then what will happen? Then one solution would quickly accumulate positive charge and the other will accumulate negative charge. So as a result, the reaction will be, there will be a halt to the reaction. It will stop. So if the reaction is stopped, there will be generation of electricity. There will be, that is the generation of electricity, that will also be stopped. So that is why it is important to insert a salt bridge. That is the second connection. It helps to build electrical neutrality. So here we have taken KNO3, but other examples are also there. So two types of salt bridge may be there. The picture that you are seeing here, it is glass tube bridge. So it is made of glass. Fine. And this U-shaped glass, that is filled with the electrolyte such as NaCl, KCl, NaNO3. And don't think that you just take any of the electrolyte. There are some specific criteria. If that criteria are maintained by the electrolyte, then only we can use them in the Sol bridge. So what are those criteria? The first is they must be relatively unreactive with other chemicals in the cell. And the second point is the cations and the anions having similar migratory speed. That is, migratory speed means suppose we have taken, that is NO3 and K plus here that we have taken, their migratory speed are very close to each other, but suppose migratory speed of NO3 minus is higher, then what will happen? There will be now excess negative charge in the left hand side, but that is not wanted. So that is why we have to choose the electrolyte in such a way so that the cation and the anion, their migratory speed is same, so that their movement towards both sides can be same. Now migratory speed same means comparable ion charge and molecular weight. So the anion and cation, their ion charge should be comparable and molecular weight should be close. Okay, and this electrolyte, that is KCl, NaCl, KNO3, whatever we are taking, that must be in the that is held in a gel, because a salt solution could easily diffuse into the cell, so that this salt solution they cannot diffuse in the other cell. So that is why the salt bridge inside there is gel. So this is one type of salt bridge that you will see. It is the most common salt bridge, but there is another type of salt bridge which is filter prepare bridge. So in filter prepare bridge it is very simple actually. Simply there is a filter paper or any other porous material which is soaked in the electrolyte. That is this electrolyte NaCl, KCl, NaNO3, KNO3, all this. Okay, so this is another type of salt bridge. So this is number 1 type, this is number 2 type. Okay, now we will come to the electrolytic cell. So in electrolytic cell, now the opposite process will take place. Now electrical energy will be converted to chemical energy, okay, to bring about the non-spontaneous reactions. So in electrolytic cell, an external source of electric energy is required so that we can forcefully produce a potential difference between these two electrons. And remember, one thing I forgot to mention, in the previous case, that is in galvanic cell, anode is given negative sign and cathode is given positive sign, but now it is opposite. Now why it is so? Because in galvanic cell, in anode, the example that we have just discussed, that is zinc is converted to Zn2+. So zinc is actually leaving some electron, and these electrons are moving towards the other side. So that means zinc, it is giving the, as it is a source of electrons, so that is why anode is negative and cathode is positive. But here electrons are not, that is we are getting the electrons not naturally from the chemical species but forcefully. Okay, so as here forcefully the electron is removed from the anode, so that is why it is now given positive sign. Otherwise it is common thing for both the cell that in anode there is oxidation taking place. Here also oxidation taking place in the anode, left hand side. In galvanic cell also it is taking place in the anode, but sign is opposite. Okay, so this forces the electrons to flow so that they can undergo non-spontaneous redox reaction. So only a single compartment is employed in most applications. In the previous case we have seen two different compartments are present, right? But now there is a most of the time there is a single compartment. So you can see there is no separation line here in this electrocell. It is a common compartment. Okay, and this is the supply of electrical energy. So remember, in both kinds of electrochemical cell, anode is the electrode where oxidation half reaction is going on, and cathode where reduction half reaction is going on. Now electrolysis, this is actually the application part of electrolytic cell. In electrolysis, we use obviously electrical energy to produce chemical energy. Now electrolysis, electro means electricity and lysis means kill. That means the phenomenon of separating a compound into its participating or constituent elements. Okay, so here we will take the example of sodium chloride. So you have taken NaCl, and electrolysis means now they are separated to Na plus and Cl minus. So the separation of a compound into its participating or constituent elements. See, these are not elements, these are ions. But suppose you are getting Na, that is sodium atom, neutral sodium atom, and chlorine gas. That means now they are element, constituent element. So we can produce these constituent elements by passing electric current through its molten condition or aqueous solution. Okay, so both are possible. We can take the molten NaCl, that is fused NaCl, or we can take the aqueous solution of NaCl. So we will see both the examples, because depending on whether you have taken molten NaCl and aqueous solution of NaCl, there will be different types of results. Okay, so first we will see what happens when we have taken molten NaCl. So here no traces of water you will find. There is only molten NaCl. Here you can see dotted line. So sometimes there is a separation of compartment, sometimes there is not. So it is not necessary. But in galvanic cell there is always separate container used. Molten NaCl, that is liquid state, it is placed into the container, and now we are using inert electrode. So we are not using any sodium electrode or any other metal electrode. We are using inert electrode because we do not want here that the electrode is taking part in the reaction. We will also discuss that there are different types of electrode you can use. In galvanic cell you have seen the electrode zinc and copper, right? But don't think that it is limited to only metal. There may be some other types of electrodes also. So you right now you can see we are using carbon electrode. Okay, that is graphite electrode. So it is inert. It will not take part in the reaction. Its purpose is only that is through it electron will move. That's it. Nothing else. So these inert electrodes are inserted attached to the positive and the negative terminal of the battery, and electrolytic reaction will occur. So Cl, as electrons are moving from this side, that means chlorine, that is chloride, Cl minus, it is leaving the electrons and itself will be converted to chlorine atom first, and then chlorine atom, two chlorine atom will combine together to make chlorine molecule, that is gas. So here you can find chlorine bubbles. Basically it is Cl2 bubbles, that is the gaseous bubbles, because ultimately Cl atom is converted to Cl2. So obviously there will be bubbles of chlorine gas. Okay, so these are the bubbles of chlorine gas. And in the right hand side, Na plus, that will accept this electron which is coming from left hand side, and itself will be converted to sodium. Okay, so sodium, we are getting the element sodium. So constituent element of NaCl is sodium element and chlorine element. So we can get both of them. So sodium ions, they are migrating towards the cathode, because in the electrolyte we have Na plus ion. Electrons from the negative terminal travel to the cathode. So from the negative terminal electrons are traveling towards cathode, and they are used to reduce Na plus ions into Na. And the negative Cl minus ions migrates towards anode, that is this one, and they release the electrons and itself will be oxidized to form Cl. So here Cl minus is converted to Cl plus electron. Okay, so here we have the reactions, that is cathode, which is negative electrode, because here electrons are pushed towards this side. Okay, so 2 sodium plus, sorry, it will not be aqueous, it is molten. Okay, so 2 Na plus accepting electron, it is converted to sodium solid, that is metallic sodium, and chlorine, that is chloride, that is converted to Cl2 gas and 2 electron. So first you can also write it as if there is generation of 2 chlorine atom and 2 electron, and then these 2 chlorine atom combine together to make chlorine gas molecule. Okay, So in this way, if we do electrolysis by taking molten NaCl, we will get sodium, metallic sodium and chlorine gas. Both will be produced. But electrolysis, as I have said, it is also possible when we have taken aqueous NaCl. So it is very important that whether you have taken aqueous or molten NaCl, because if an aqueous solution were used in the above system, result obviously it is not same. So that is why it is important to mention whether you have taken molten NaCl or aqueous NaCl. So in aqueous NaCl, obviously now except Na+, there is also presence of water. So as there is presence of water, what will happen? The aqueous solution of NaCl, it will contain Na plus Cl minus and also H plus HO minus from this type of dissociation. Okay. Now compared to NaCl, obviously water is weak electrolyte, so its dissociation will not be complete. So ion population of H plus and HO minus which is coming from water, obviously it will be less compared to Na plus and Cl minus. Now here we have two cation, that is Na plus and H plus, and we have two anion, chloride and hydroxide. So the cations, that is sodium plus and H plus ions, they will move towards a negative electrode, that is cathode, and anion Cl minus and HO minus, they will move towards positive electrode or anode. Now there is a competition between these two, that is, as there are two ions, in the previous case there is only one cation, so no question of competition, but now you have Na plus and also H plus. Then who will accept electron? Is it H plus or Na plus? Now here there is a list of values of electrode potential. From these values we can understand that whether some specific system will be reduced compared to the other system, and that table or list, whatever you say, that is known as electrochemical series. We will discuss that, but not now. But right now just remember that there is some specific values at least mentioned in the table, where from, that is just by checking the values you can understand that which one will be reduced or which one will be oxidized. So it is observed that the tendency of H plus to accept electron, it is high compared to Na plus. So that is the reason only H plus will be reduced, not Na plus. Okay, and among Cl minus and HO minus, only one anion will be giving electron. Okay, and that is also dependent on their value, because for each system there is a specific value, and from the value we can understand that which one will be reduced. Normally it is observed that higher is the value of reduction potential for each half cell, higher is the tendency to act as oxidizing agent. That means higher is the tendency to accept electron. So if I am saying that here H plus is accepting electron, that means H plus should have higher reduction potential value compared to Na plus. So here at cathode, between H plus and Na plus ions, H plus ions are discharged, and on the same ground, that is, as Cl minus is winning the competition, so Cl minus ions are discharged in preference to HO minus. So it means what? Na plus will remain as Na plus, and HO minus, that will remain as HO minus, because they are not taking going towards cathode or anode. So these Na plus and HO minus which are remaining undisturbed in the aqueous solution, so they will be present as NaOH. So if you are evaporating the solution, because it is water solution, if you are evaporating it, water will be removed and you will get crystals of NaOH. So by this method you can produce sodium hydroxide. Okay. So at cathode, the reaction that is going on, first H plus is accepting electron, it is converted to hydrogen atom, and two hydrogen atom now making H2 molecule. And similarly at anode, Cl minus is leaving electron, two Cl atom combining together to make chlorine molecule. Now this is the picture of the electrolysis of aqueous NaCl. Here we have taken aqueous NaCl, and in the anode only Cl minus is moving, HO minus is still there, and in cathode side, actually you can also consider it as if it is H plus. So H2 is mentioned, basically it is H plus. So here, sorry, it will be NaCl remaining and HO minus remaining. So these two together will make NaOH. So see, now both side gaseous molecules are generated, because in the left hand side chlorine gas is generated. That also we have already seen in case of molten NaCl. So same case are happening, same thing happening here also. That is, in the anode side you are getting chlorine gas, but here in the cathode side we are not getting sodium metal, but instead we are getting hydrogen gas. So both side there is bubbles of gas. Left hand side chlorine gas, right hand side hydrogen gas. Okay, and here also we have taken inert electrode, just as we have taken in case of molten NaCl. So carbon electrode, which is the inert electrode that is used. So here we can generate hydrogen, we can generate chlorine gas, and also we can generate NaOH. Okay, so these are the important applications. So when we are doing electrolysis of aqueous NaCl, you are getting chlorine, hydrogen and sodium hydroxide. So now, as we have discussed in detail the galvanic cell and electrolytic cell, now we will try to compare them. So there are some, it is not that all the points will be different, there are some common points and there is some points which are dissimilar. So in galvanic cell, the main important difference is here chemical energy converted to electrical energy, but here the opposite is the case. The redox reaction is spontaneous because it has to be spontaneous, otherwise how we can generate chemical energy. So it is responsible for the production of electrical energy. And in this side electrolytic cell, redox reaction is not spontaneous, and that is why we are providing electrical energy so that we can start the reaction. The two half cells are set up in different container being connected through the Sol bridge or porous partition, but here we are not using any Sol bridge. We are taking it in the same container, molten or aqueous electrolyte. And if we talk about cathode or anode, here anode is negative, cathode is positive. Here it is opposite, anode positive, cathode negative. But the common point is in both cases, in anode there is oxidation, cathode reduction. That is the common point. Okay. Another table I have added here. So in a nutshell, if we see the role of this cathode and anode, what are their signs? So if it is galvanic, sign is positive, this is negative. And remember, here it will function as electron acceptor. Remember, in galvanic cell, Cu2 plus is accepting electron and it is converted to metallic copper. And in the anode, electron donor, that means Zn is giving electron to and itself is converted to Zn2 plus. So it is acting as electron donor. But when it is electrolytic, cation attracting. Remember, in the previous slide we have seen that in the cathode side, cation attracting means you can also say cation reducing. So H plus is attracted towards cathode, and in the left hand side, anion, that is Cl minus, that is attracted towards the anode. So that is why you can say that now it is in terms of ion, not electron. This is cation reducing, this is anion oxidizing. Okay, so try to remember this table. Now representation of galvanic cell. So mostly we will talk about galvanic cell. So how we can represent it? Already we have seen that oxidation is taking place in the anode. So this example is for Daniell. Remember, in Daniell we have taken zinc and copper system. So oxidation will take place in the anode side, which is when you are drawing the cell diagram, it is in the left hand side. And when you are representing the cell, then also it is in the left hand side, and reduction in the right hand side. This parallel sign that you are seeing here, this is signifying the salt bridge, that is the junction between the two half reaction. And Zn and Zn2 plus, here concentration of Zn2 plus is given because it is the salt. Suppose zinc nitrate or zinc sulfate is there. So this is the concentration of the electrolyte. And in this side, it is the concentration of the electrolyte, which is copper sulfate or copper nitrate. Okay. So concentration of aqueous solution. And another important thing is, if you are confused that whether to write Zn2 plus first or Zn, you have to write Zn first. Why? Because Zn is converted to Zn2 plus, not the reverse one. So reactants are listed before the products. And Cu2 plus is accepting electron and it is produced to copper. So that is why Cu2 plus is written first and then copper. And here we are using one single vertical line, because double line means it will be salt rich. And also see, here we have not used any inert electrode. Here the metal itself is the electrode. So here zinc is the electrode, copper is the electrode. So when you are representing the cell, first you have to mention the electrode, and as here our electrode which is zinc and the metal cation, that is also zinc, both are same. Suppose if instead of zinc you have used platinum, then you have to write platinum here. But we have not used that any separate electrode. We have used the same cation electron, that is why Zn will be written here. Now we will see another example of cell representation, which is to some extent different. Now what is the difference? See, now in the anode side, this reaction is taking place. That is, hydrogen is converted to H plus. And here as gaseous material is there, solid hydrogen is not possible. Then how it will play as electrode? So that is why we have used separate electrode, which is itself is not taking part in the reaction. It is inert, but its presence is required. And in the right hand side, cathode, Cu2 plus accepting electron, it is converted to copper. So copper, as it is solid, so now it can be used as electrode. So we are not using any separate electrode. And this is the net reaction. In the reaction, you don't have to mention this electrode because it is not taking part in the reaction. Here it is simply mentioned aqueous. Sometimes concentration it will be given, it may not be given. Okay. And states are also mentioned. So if molarity is given, that means obviously it is aqueous solution. If gaseous it is written, then instead of concentration, the pressure will be mentioned, because we know that electrode potential is dependent on the concentration. But in case of gas, there is no concentration, only pressure will be used in terms of atmosphere unit. So in that case, pressure of hydrogen will be important. Okay. So here there is no metal in the left hand side, but there is gas. H plus is produced from H2. So here H2 is actually the reducing agent and copper is the oxidizing agent. Okay. In the other case, in the previous case, in aqueous solution of NaCl, when we are seeing the electrolysis reaction, there we have seen H plus is accepting electron, but now it is giving electron. So it depends with which other system, that is depending on the other half cell with which it is attached, depending on that it can be anode or it can be cathode. So as I have said, from the electrochemical series where all the values are mentioned, from the values you can understand which will act as anode, which will act as cathode. And how to measure the EMF of the cell? If you want to measure it, you have to write the electrode potential of anode and electrode potential of cathode. Now, as I have said already, by IUPAC convention, if nothing is mentioned, it is simply the reduction potential of cathode. But if you are writing oxidation potential of anode, and if you want to convert it to reduction potential of anode, numerical value will remain same. It will be simply the change of sign. So if oxidation potential of anode is X, it will be minus X. Okay. So we always prefer to mention all the electrode potential in reduction potential term, not in oxidation potential. But in some numerical, or if you are seeing any discussion related to electrode potential, if it is oxidation potential, it will be mentioned separately. But if it is not mentioned, you have to consider it is reduction potential. So oxidation potential you are converting to minus reduction potential of anode, and now this is actually cathode. It is present in the right hand side, right? and this is present in the left hand side. So you can also write it as E right, that is electrode potential of the right hand side system. That is, here copper system will be written first and then the left hand side system, because there is a negative sign now, as if this is actually E left, but there is a negative sign. So that is why if you are bringing it next to Rp of cathode, the final expression will be like that. So individual reduction potential of these two systems will be there. So if you know the individual values, reduction potential values of both the system, you can get the combined EMF of the cell by applying this formula, that is reduction potential of the right hand side system minus reduction potential of the left hand side system. Okay,